Hello all. So, in this lecture, we will be mainly discussing about a new type of material which is called ferrometamaterial, and it is being mainly used for the case of sensing. So, we can name it as a ferrosense material. Now, what is this ferrometamaterial basically is? So it is actually a coupling between a ferroelectric material and a metamaterial. So a ferroelectric material or a ferroelectricity, it mainly has the following properties. It has a spontaneous polarization, which is reversible by an electric field. That means if you plot the polarization P versus electric field plot, this one. So the polarization will get reversed once you change the direction of the electric field. Secondly, it is asymmetric crystal structure like B80IO3 and PZT. Now this asymmetric, or it is also sometimes called centroasymmetric. It is not a centrosymmetric structure. So that is why when an electric field is applied, there is a shift of the center in these materials, and due to that shift, there is a distribution of positive and negative charges that take place and which give rise to the dipole. So basically, they are also piezoelectric materials, and of course, there is the hysteresis behavior associated with these ferroelectric materials. For that reason, these materials are used as memory devices and for sensing as well. Now, metamaterial, on the other hand, is, if you go by the exact definition, it is basically a material which has got artificial, uh, it is an artificial structured and tailored material with different electromagnetic properties. Now, the foremost property, or the very important property associated with the metamaterial, is the negative refractive index. And apart from that, this metamaterial can also cause enhanced field interactions, and it is also for used in frequency selection. Now, metamaterial also basically is the one, if you go by the structure of a metamaterial, which say is giving a negative refractive index. So the main property a metamaterial should have is that it should have units. Like in a solid you have crystals, similarly to that in a metamaterial, it should have engineered units arranged in a pattern. So even if the material is not showing these sort of properties, it may show other type of property. Like it may show a property associated with, say, optical transmission, or it may show a property associated with any magnetic biasing. Okay. So the basic idea is it will have a units, artificially engineered units arranged in a pattern. Now, if we marry this ferroelectric material and a metamaterial, that means if we try to understand a metamaterial which is basically derived from the properties of ferroelectricity, then we get some interesting properties, some tunable properties, like we have dynamic permittivity, it will have field enhanced sensitivity, and it can be used for various applications like multiphysics computing. Now, there are different ways of fabrication of these metamaterial. I'm not going into the details, but they are mainly fabricated by nanostructuring, e-beam lithography, and also the thin film deposition techniques like sputtering and solder processing. And they are mainly used, as previously told, based upon these two properties. They can be used in various type of applications like environmental monitoring, that is detecting of pollutants with high precision. Then it can be also be used for biomedical diagnostics, biosensors, and also Internet of Things. Now, a metamaterial, an example, let's start with an example of metamaterial. A metamaterial can be said to be having a porous structure, like in this case. This sort of metamaterial is called sphenoids. Now, how we are actually defining a sphenoid? We are defining a sphenoid by a Gaussian random function, which is mainly given by this phi x term, where x is the wave vector. Now, if this phi x term, and we are trying another parameter called gx, which is a binary parameter. So, if this will have two different values, one is when the material is in the solid state, and one when there is air or void. So with these two different values, we can theoretically think of a material which is having a patterned porous structure. So this corresponds to a porous ferroelectric material. So similar to this, we can also have different types of ferroelectric material for different applications, like the one which is shown here, where it can be used for, where a metamaterial has been used for formation of, in the case of an atomic force microscope. Okay, so basically this is very basic introduction to ferroelectric metamaterials. One has to go very deep and to very complex mathematical simulations, and the experiments are also very complicated in nature to produce devices based upon these ferro sensing material of that high precision. So I will try to give few examples of these ferroelectric metamaterials in my subsequent talks. Thank you.